Well, thank you, Seth. I'm going to try without the mic. Probably going to be a bit easier for me. It's great to be here. I'm really glad to be here. And of course, I'm particularly honored to be opening up this great event for you guys with this talk on Akka HTTP. It's always nice for me to come back to Boston, first because I've studied in Massachusetts a long time ago, and second because it was actually in Boston at NE Scala 2012 that I did the very first public talk on Spray. A lot of stuff has happened since then. Of course, we've moved a lot forward, and it was quite a ride actually. But this talk is still on YouTube, and you can also find the link on the Spray website. And if you haven't seen it yet, then I would totally recommend you keep it that way because the talk isn't very good. So, we were actually quite surprised about the amount of uptake and interest in this HTTP library that we've developed. And we weren't really quite sure initially where all this is coming from. Like, where does all the interest come from? Why does everyone really always ask us about presenting and talking at conferences and so on? But when you think about it, you realize, well, there's a good reason why we all need a proper HTTP stack. Right? And the reason, the ultimate driver for that is the same as it's probably for a lot of the talks that we're going to see in the next 2 days. The world has changed significantly. As you all know, we now live in a multi-everything world, multi-threaded, multi-cored, multi-machined, multi-data centered, which has the effect that all our applications are now distributed. They are, and this is the core driver for a lot of developments also in the Scala world. They really are distributed, even if they are just distributed across threads and cores. And it makes sense sometimes to, even at that level, think about your application as being a distributed application. But it's not just across threads and cores, it's across machines and data centers, across organizations, and essentially across the world, right? If we build an application today, we certainly don't live on an island anymore. We are going to talk to the world in one shape or form. And that distribution is the core. And since it's an Akka talk, let's look at what the Akka toolkit promises. When you go to Akka.io, you see the promise that Akka put up, and that's to make it easier to build powerful concurrent and distributed applications. That's what Akka wants to do, right? And because distribution is the core of everything we do now, it's important. There are two big things, concurrency and distribution. And when you think about distribution, then this always implies integration, right? If I distribute stuff, I need to integrate the stuff that I've just distributed. And since Akka is the toolkit, there is distribution, for example, within one machine, just across threads and cores, and Akka gives you a tool to work with that. It's not the only one. You cannot, Akka actors are one possible way to deal with the challenges of programming concurrently. There are many other tools, but Akka gives you one. If you are outside of one machine between your own subsystems that you control, then Akka gives you things like Akka remoting and Akka cluster to integrate the different parts of your whole application. And of course, when you talk to other external systems that you don't control, that's where Akka HTTP comes in. That's where it makes sense for Akka to take on an HTTP module, because integration with the rest of the world probably is going to happen through HTTP. Now, it is the most successful integration protocol up to now. It's not perfect. It has all kinds of warts, and there are many good reasons to critique HTTP, but it's the standard. It's what everyone needs to talk, and so our systems need HTTP in order to be able to integrate with the rest of the world. All right. So when we look at Akka HTTP, there are certain things that make it cool, right? Why is it cool? The design goals that have flown into this they come from the learnings of the last years, and of course we want to achieve maximum throughput with acceptable latency. Right, that's what you're looking for. You want performance. We want to be able to properly scale across all our cores, crank up the machine, really use it properly, and basically give you an unlimited number of connections, unlimited in the sense that you're limited by your memory, by your by your operating system, but not by the library, the HTTP stack that you use. One important thing is that we always had in Spray and in Akka HTTP server and client-side support at the same time, because integration with other systems means you need to consume as well as provide services, right? And it's not enough to just focus on one side. Then, of course, what you expect from a modern library is open composable APIs. You want to be able to easily integrate it into your stack, into whatever you choose. It shouldn't be hard to work with. It should nicely allow you to factor out things and so on. So that's important, and commonly, as is en vogue, it's indeed not a framework style, right? You probably have heard that before. And our focus with this layer is integration. As I said, it's integration. It's not necessarily building web applications. There are certain differences. You can use it to build web applications if you really want to, or if your application needs are simple. But if you know that the core of your application is the interaction with the browser, then things like Play might be better suited. All right, so if that are the goals, they have certain consequences for the implementation. And it means if we want to scale, if we want to really get high performance, we need to be fully asynchronous and non-blocking, right? There's no way around that, otherwise we won't scale. And since we're in Akka, it needs to be somehow actor-friendly, even though Akka HTTP is now moved a bit away from the pure actor basis. It's still implemented on top of actors, but that might change, and you don't need to worry about that. And the current APIs are actually not actor APIs anymore. Of course, it needs to be lightweight, modular, testable, everything that you expect. And it's fully, well, is that even a word? I'm not sure, this thing. You can decouple it from the underlying TCP interface, and we're going to see what that means. And as you know, it's based on Spray.io, so we built on top of the experience there, reused whatever was possible from the code base, but also wrote a lot of code completely from scratch. So what is actually coming in from Spray as heritage, so to speak? There is a pretty good immutable case class-based HTTP model that many people have grown to like, and that didn't need a lot of adaptation. We have a very efficient parsing and rendering logic for HTTP, which is the reason, or one core reason of why Spray has been so fast. And then many people might know Spray mainly as its surface layer, which is the routing DSL on the server side, but it's only one part. And that part is going to be moving, or is moving into Akka HTTP with small tweaks, but no major changes. And there's the test kit, which is basically the same. Of course, we've learned over the last years a few things that weren't as great in Spray. And they are centered around a common theme, which is mostly a lack of having the right, just having the right abstraction. We didn't have the right abstraction to tackle a few of those weaknesses. If you've worked with Spray, then you might know that handling chunked messages, requests, and responses can be a bit clunky. It's not as easy as it should be. Dealing with large messages kind of is similar. It's sometimes hard, and we're going to see a little bit later what exactly can be the problem there. Then the routing DSL has its own kind of small traps that you can fall into if you're kind of new to Scala especially, and there are things that we can improve. And of course, if you come into Scala, then you sometimes have trouble with implicit debugging and these kind of things, and missing features are always a thing. There's always a weakness. We'll always have missing features. One common one is WebSocket support for Spray. So there's one example that I want to go into a bit deeper. Because we have the ability to work on the client as well as on the server side, proxying requests is actually quite easy, because you work with the same kind of data models on the one and on the other side. So this is a scenario that has come up quite a few times over the last years, where someone said, wow, cool, we have this new backend written completely in Scala, we use Spray for it, it's all great. But small parts of our application, they still need to run. We just keep it running on a legacy machine, on the same LAN, it runs whatever, Django or whatever. And for certain types of requests, we need to proxy the request over to the legacy backend and just funnel the response back to the client. So that's what it usually looks like. You have a client that requests something. We proxy the request over to the legacy backend. The legacy backend answers, proxies the response back to the client, done. You can build that easy. Now, you can see where the problem comes in if the response is really, really large, because you have a disparity in data rate, right? The LAN is fast, and the client might be in New Zealand, really, really slow. And you can see where the problem is. It's there, right? You have a risk of getting squeezed there, because the legacy backend might just dump the 8 gigabytes across a 10 gigabit connection onto you, but you actually need to spoon feed it to the client, right? So how do you solve that? What we need is pushback. We need to somehow slow down the legacy backend in sending stuff to us. Now, TCP, the underlying transport, can do that, but your stack in Spray, your HTTP stack, needs to handle that properly. And this is tougher than necessary with Spray. It's possible, but it's brittle, it's not really robust, and it doesn't work in a composable way. And that sucks. That's one of the main problems that we needed to solve. So Akka HTTP is something like Spray 2.0. Right? We address the weaknesses. We do across-the-board publishing. We add Java APIs for everything, which is something that we've tried to avoid all the time in Spray, and now we can't avoid it anymore. Everything in Akka has a Java API, so Akka HTTP needs to have one as well. We've simplified the module structure a bit, but there's one core improvement, and that's that we moved a lot of the core code onto Reactive Streams. The Reactive Streams is basically the basis of everything underneath Akka HTTP and the new Akka I/O. I don't really have the time to go into Reactive Streams too much today here in this session, but I'm going to be offering a session on Reactive Streams tomorrow. I have a lot of material that I've been presenting several times across Europe in the last month, so if anyone's interested, tomorrow we can have a deep dive into Reactive Streams. So today, just one chart, Reactive Streams, all you need to understand at a very high level in order to be following the rest of the talk. Reactive Streams are basically a new abstraction for asynchronous and non-blocking pipeline processing. If you do pipeline processing in a synchronous way, then you always can resort to blocking, and that kind of solves the back pressure problem. But if you're asynchronous and you don't block, then handling back pressure in a similar way that I've just shown, slowing down the source of the data that you're digesting, is tougher than you might initially think. And Reactive Streams is one attempt to do that properly. The core improvement over prior works like RxJava is that the big back pressure is built in and handled properly across everything. And tomorrow we're going to look at that tomorrow, really in depth if you're interested. The Reactive Streams project itself defines not much more than just an API that different implementations can implement. And the core goal is to have all the different implementations of Reactive Streams be interoperable, so that Twitter can have their implementation talk to the one from Netflix, talk to the one from TypeSafe, and so on. So that's great. There are many, many use cases for Reactive Streams. And as I said, it's a joint effort from big shot guys from important companies. So back to Akka HTTP, where do we have streams? There are quite a few places where streams are important in Akka HTTP. Of course, you can think about the requests that come across one connection as a stream. It's a stream of requests that comes out. And on the other way, what is going out is a stream of responses going out across the same connection. If you have a request, then the entity, so the content of the request, can be chunks, a stream of chunks. And if you model that as a proper stream, then it's the same abstraction, again, just one nested level in. And the bytes, if it's not chunked, if it's just a raw request, then even the bytes of this request or response can be looked at as a pure stream. So these are the 4 major points where we have streams in Akka HTTP. Now this picture is actually, this is important. If you take away one thing from this talk, then it's this picture. This is what Akka HTTP gives you. Let's look at what this means. The yellow stuff here is your application, right? On the client or on the server side or on both sides. And the stuff in the middle is what Akka HTTP gives you. Now let's look at the client side first. you basically have some kind of processing pipeline where you implement your business logic that does certain things to whatever data you are dealing with. And what Akka HTTP gives you on the client side is an element that you can plug into your stream logic that transforms requests into responses. Because that's essentially what a HTTP client does, right? It's a function, essentially, asynchronous, non-blocking, properly modeled function that you stuff in requests and you get out responses. That's it. That's a client. And on the server side, it's exactly the opposite. What you provide as a server is a function, more or less, that turns requests into responses. That's what you build. And if you stay within the stream abstraction, then on the server side, you provide a piece of pipeline that properly connects onto those sockets and that transforms requests into responses. And on the client side, you need a piece of pipeline from the library that transforms requests into responses. But this is all streamified. It's all streams. Now the benefit is, for example, let's look at what this means. Suppose here the client pipeline has some slow stages, something that takes a long time to process because you're doing expensive CRC checking of the content of the response or something. So if this is slow, then this stream abstraction makes it possible that this back pressure that is building up, so that the slow down signal, gets carried across this part of the TCP connection, and TCP does have flow control, so we can use that. All the way here, it slows down the server in producing responses. Now, if the server is built properly with Akka HTTP on this side, then this back pressure will actually carry over to this side, go across here, and slow down the client in sending requests. So the client can, because this stage is slow, maybe this stage is being slowed down, right? And that's important because you need to stay, if you rip up the pipeline somewhere, then you're going to have data loss or you're going to have out-of-memory errors or whatever. So if you stay within this tight stream pipeline, then the back pressure will properly carry over all the way to wherever the data are coming from. And that's really nice. And that solves the problem that we've seen in the beginning by just automatically slowing down whoever is sending the data. So if we do a double click on this thing, I've shown it as just one element, but it's of course several elements. So this is the stack of what it is. You have underneath obviously the operating system, then you have the NIO JDK currently as our basis layer. And then you have 2 or 3 layers on top. There's Akka IO, which is a module that has been in Akka for a year or 2, I think, that implements the translation between the raw NIO interfaces and a proper actorized message-based TCP UDP interface or a proper streamified TCP interface, right? So you get stream interfaces for TCP. On top, we have Akka HTTP core, which does just the translation between TCP and HTTP, right? That's it. That's all it does. And your application can choose to sit directly on the core layer and not use this part, which is the higher level stuff like the routing DSL and marshalling, compression, all these kind of things. And Akka Stream, which is also in the new Akka module, kind of sits on the side because it's a helper technology that is used across all stacks. It provides the stream infrastructure that is needed here and here and here, and potentially also at the application level. You can choose to build your application with Akka Stream if you want to. You don't have to, but if so, then you'll be using that as well. So now I have a few charts that just do explain what I just explained as well. So that's Akka IO, Akka HTTP core, what I just said, and the responsibilities of the Akka HTTP layer. So there's one, before we dive into the code, finally, there are a few basic concepts that we need to understand in order to be able to understand the code that's coming. And tomorrow we're going to dig into that deeper if you're interested. So there are a few things that are important. A source in Akka Stream is the open end of a pipeline. So you have a stream pipeline that can produce T's if you ask it to produce T's, and that's a source of T. And a sink is just the opposite. You have a piece of pipeline that you can stuff T's in if it requests them from you. And a flow is basically just a piece of pipeline with two open ends. So with a flow, you can take a source, plug in a flow, and then you have a new source here, right? You can put in another flow, and then you have a new source at this end. And in the end, you need to somehow connect it to a sink, and once you have it connected to a sink, the whole thing is done, and you can push the button and say go, right? That's roughly the logic of how this works. And there's one important thing. Generally in Akka Stream, sources and sinks and flows are reusable. Meaning if I have a piece of flow, for example, I can take one source, plug it in, start it, connect it to a sink, start it, and then take the same flow instance that I still have, plug it into another source and another sink, and then crank it again. So you can materialize a stream several times. That's the concept of materialization. It's important to understand that concept before we can understand the code. So materialization is take the template, a source, a flow, a sink, put it together, and then when you push the button, that's materialization. You can push it several times, and you get several materializations, incarnations of the same stream. OK, so let's look at the server API. What does it look like right now? So it gives you, Akka HTTP gives you a bind method. And the bind method takes an endpoint and a bunch of settings, doesn't matter. And it immediately gives you back a server binding instance. So there's no future here, and nothing really happens at that point. You just get a binding, right? So you have a binding. What can you do with a binding? A binding gives you a source of connections. Because in the end, you can look at a server, as a TCP server or HTTP server, as something that produces connections, right? So and they are modeled as a source as well. So it's a stream of incoming connection. And when you materialize this source, that's when the binding happens, right? Up until that point, the binding doesn't happen. Now, you can take the same binding and actually bind several times, materialize several times if you want to. Now, if you have a concrete port, that won't work. The second time you try to bind a port, it won't work. But if you bind to port 0, for example, the operating system is going to assign a port, the free port, and you can actually bind 10 times or 100 times if you want to, for the same server binding. So let's just skip across the rest. There's a bit of sugar here, but that's the basic idea. Now let's look at what do I get out of this source once I've materialized it? What is an incoming connection? An incoming connection is this guy. It has, at the time you see it, at the time you have an instance in your hand, the connection has been accepted. So you have a local address and a remote address right there. And what you then do, we're on the server side, you can call handle with a handler and a flow. So what you supply, as we've seen, is the piece of pipeline that translates requests into responses. And if you give that to the incoming connection, then the connection will take that, attach it to the socket, and have it run, right? That's it. And you can take the same flow instance for another connection and just have it materialize there, right? So that's why it's important that you can reuse flows, because you can supply a flow once, and then it can be materialized for every connection again and again and again. And there's a bit of sugar here that we're going to see tomorrow, how that is implemented. This is just one line. It just helps you to, if you don't want to stay within the flow and you already have a true function, a synchronous function that translates requests into responses, you can just use that. Or if you have an asynchronous function that produces a future on a response, you can just use that. Obviously, streams and futures, they interoperate nicely, and there's all kinds of things that make it easy for you. So there's one more interesting bit, which is there's a function that allows you to use the HTTP layer all by itself. And what it does is you give it the flow, the server flow that translates requests into responses, and what you get back is another flow that you can use on the underlying TCP layer. So because the Akka I/O layer gives you essentially exactly the same APIs, not from request to response, but from byte string to byte string, because that's what TCP is, right? So and if you use that, that basically just translates or encapsulates everything that the HTTP layer does, which is parsing requests and rendering responses all by itself. And then the nice benefit is you now have a flow that you can plug into the TCP layer if you want to, but you could also just materialize it in your tests just for yourself and you know, just use your own byte strings and just run the HTTP layer detached from everything else. And that's really nice. It's completely decoupled, and it allows you to just work with this in a much nicer way than it's been possible with Spray or with other libraries or frameworks. Okay. This is a very simple example. It just uses the what would it look like to have a small ping pong server. So you have a binding, and then you just call this sugar method, which does this. And you can probably all understand what this does. So that's of course it's a bit of cheating because we just put all the hard stuff in there, but this is just one line. So and tomorrow we'll see how that looks like underneath. So on the client side, let's move over to the client side. On the client side, you call outgoing connection to an endpoint, and you get back an outgoing connection instance. Again, no connection is actually being established. Nothing happens at that point. You immediately and synchronously get back an outgoing connection. And only when you take the flow that is part of this, plug it into your stream setup, and then materialize that, then the connection is established. And that can happen several times. You can take this out. Actually, the name, we should improve the name. It's, if you take this instance here and you materialize it 10 times, 10 new connections to the host will be opened, right? Because you can just open several connections. And on the client side as well, there is the ability to separate the HTTP layer from everything else, and it's just the other way around. So you give it a transport on the TCP level, and what you get is the upgraded flow, the upgraded piece of pipeline that includes the request rendering and the response parsing on the client side. Again, this is great for testing. Okay, so the HTTP model is very similar to what we have in Spray. So if you used Spray, who of you has used Spray actually so far? Many of you. Okay, great. Then this will all be very familiar. It's more or less the same. There was no reason to change a lot of the things because we already got it kind of right the first time. It's high-level abstractions for most things that you work with. It's immutable, little logic there, and it just gives you the core types and singletons and definitions that you need, and it's open for extension. This is the request in Akka HTTP. It looks very much the same as in Spray, so it's properly typed as you would expect in Scala. So the method is not a string; it's a proper type, and the URI is a proper type, and so there's no stringly typing here. The HTTP headers. There's one difference to Spray is that now the entity here is a request entity, and we're going to see that in a second what that means. On the response side, we have a status code, which is not an integer, it's a proper type, and so on, the same kind of headers. And here we have a response entity, right? The entity of an HTTP response. And this is just to show that even the URI is another time properly typed. So we have proper types for the authority, for the path, for the query. So there's a lot of deep model here that gives you safety when working with URIs and just everything in HTTP, which is great. So the entity is interesting because that's where a big change over Spray has happened. So let's understand this. So there's a supertype HTTP entity, and then we have a response entity, which you can use on responses. Then we have a request entity that is used for requests. And what is interesting and what trips people up is request entity, it extends response entity. Now, what does that mean? Does that even make sense? It does make sense because what it means is that everything that comes in a request, you can also use on the response side. So if I see a request, I can take the entity and put it in a response, and it's all fine. But it's not the case the other way around. And we're going to see why. So anything I can use for any type of message is a message entity, and it's just an alias for this guy. And then HTTP, what an important feature that is used very often is multi-part messages, where several smaller content pieces are chunked together into one big request or response. Commonly, for example, for forms or for file upload, that's a type that you would use. And there's entities, again, inside of those parts of a multi-part message, and that's a body part entity. And a universal entity you can use anywhere, right? Because it's just standard. So let's see, there are 5 different incarnations of these guys. The first one is a strict entity, which is a universal entity. You can use it anywhere. It has a content type, and it has a byte string. So if I already have the data in memory, if I already have the string, there's no point in creating a complicated stream abstraction around it. I want to be able to use it just like that. So many times you will just use a strict entity. But it's not the most general one. The most general one is this one. It has a content type, it has a content length, because you need to know a priori what is the length of the whole guy, and then you have a source of byte string. So a stream that you can instantiate, also materialize, where you can pull out the data. But you don't need to. If you don't want to read it, then it's going to stay where it is. If you don't open up this data source, then the stack will actually not read the stuff from the socket, and the client or whoever is on the other side will not be able to send the data because you're not reading it, right? That's where the back pressure comes in. But you can already look at the rest of the request or at the response, for example, the headers or the URI, even before the entity has been read off the network. That's a big improvement over what we have in Spray. So a chunked entity models the chunk transfer encoding in HTTP. It has a content type, no content length, because chunked messages don't have a content length header. And it has a source of chunks, right? I'm not showing the chunk stream part. It's basically just chunks, with the exception that the last chunk in HTTP can have additional data like a trailer, additional headers, and funky stuff that rarely is used. So, and this is a message entity, meaning that you can use it in requests, in responses, but not in body parts. Because in body parts, it doesn't make sense to have chunked in there. That's clear. Now, this guy is strange because this guy is a response entity. You can only use it on responses, not on requests. It has a content type, no content length, and a source of byte string. What this is the exception that we have inherited from HTTP 1.0, which allowed an implicit ending of a response by just terminating the connection. So HTTP 1.0 allows the server to send the response and then at the end just terminate the connection, which isn't a great idea because the connection might have been, closed for whatever reasons, not necessarily for the right reason, and you don't have a way as a client to figure out, was this a mistake, an error, or is that the proper ending of the response? So that's discouraged in HTTP 1.1, but it's still around and tons of clients and servers rely on that, so we need to model it. And obviously you can only use it for responses, because closing the connection at the end of the request kind of defeats the purpose. You can't read the response then. So that's why there is a difference between what is allowed on the request and what is on the response side. And then in the end, we have something similar just for body parts. OK, so a few headers just to show you the model, how it works. If you know Spray, that's exactly the same. We use the funky backtick notation in Spray and in Akka HTTP quite a lot because it makes it easy to understand or to think about what is the type for this header, right? If I look at a set cookie header, I need the type of the header, then I know what the type is without having to apply a certain transformation of what do I do with a dash? Is it camel cased or is it an underscore or whatever? We just use the same string and it makes it really easy. Of course, this is a problem for the Java API. Right, how do we, well, there are tons of problems with Java API. And of course, we have a raw header. We can't model everything, so there are tons of headers that we don't know about that you make up yourself, and you can still use the escape hatch of just having a string thing. This is basically all that Play does, right? Play doesn't have a strong, deep header model. It gives you string headers. So the benefits over the Spray design, we have a deeper and more properly typed model for requests, responses, and the entities inside them. In Spray, this was all kind of compressed onto the same level. You had chunks and which are actually a part of a request on the same message level as the requests themselves, which made it really tough to separate the two. Entities can now have arbitrary size properly. We're not reading them from the network unless you request them. That means we can deal with arbitrarily long messages in bounded memory, and that's great. And as I said, now a nice benefit is that you can see the request or the response as soon as the header has been read, the header part. The rest of the response can still, be in flight somewhere or sit in some buffer, and you don't care. You can already decide, do I take it? Do I read it? Do I reject the request because there's no authorization? And I don't have to read the upload that is, the 10 gigabyte upload that the client is trying to push onto us. So it's much cleaner, much nicer to be stream-based here. So there's more. Of course, I could be talking about the server-side routing DSL. It looks very similar to what you have in Spray, so no big changes there. There's testing. I could talk about in client-side APIs I haven't really shown, and the JSON. JSON is always a big question. So I'm not going to talk about that. There's the roadmap for us is, since we're on top of Akka Stream, and Akka Stream depends on Reactive Streams, on the Reactive Streams API, we're kind of, this is our upstream in terms of dependencies. And this Reactive Streams API is almost completely specified. There's an RC out, and we're going to see 1.0 very soon, which means that we have a stable specification for what Reactive Streams are like, and all the implementations can properly program against that, and then it'll be even more stable. And we are very close on finishing up the first 1.0 release of the new Akka modules, which is Akka Stream, Akka HTTP Core, and Akka HTTP. And you can see we're almost done. On the client and server side, the bottom layer is almost done. One thing that we haven't really had time for right now is the high-level client side. So there's no high-level client side right now. So if you're on the client side, you need to drop down to the connection level right now. But that's going to change. Of course, the most requested feature of Spray, WebSocket support. There are like 185 different +1s on that ticket on GitHub. So if you want to, you can put your own onto it as well. But we're going to add it. We have been kind of pushing out WebSocket support because we knew that we were going to change large parts of the underlying infrastructure. And if we had implemented that in the Spray world, we would have to re-implement everything now on top of Streams. That's why we kind of pushed it out. But now, since we have the new infrastructure underneath, it's easy to just, well, of course, it's just we're 90% done, always the case. No, we haven't really started yet, but it shouldn't take long, maybe a few weeks. We'll see. And then, of course, in the end, the goal is that Play will move onto this new shiny stack and move off Netty, which they're successfully using so far. Netty is a good project, but Netty is a different world, right? It's not Scala. It uses its own thread pools. It's configured in a completely different way. It's logging in a completely different way. So it's its own world, and there's a benefit to just unifying everything on the same kind of clean stack, and that's where Play actually wants to end up. So the goal is to build a new kind of driver for Play that sits on top of Akka HTTP, put it on the side, and let you configure which driver you want to use, the old proven Netty one or the new shiny Akka HTTP one. On top, you shouldn't feel any difference, except that the Akka HTTP one will be a lot slower right now because hasn't been any optimization so far. We've been focusing on many different things, but not on performance so far. So if you look at Akka HTTP right now, it's dog slow. But the core thing is that the architecture is very nice. And there's no reason why, in the end, we shouldn't even be faster than Spray. Because we have all kinds of optimization options that we can pull. We haven't pulled yet, so don't look at performance. In the end, we will have something that's really, really, really fast. So, and then obviously after we've matured this new driver underneath Play for some time, then we can deprecate the Netty one and then move into the new shiny world of having everything from Akka HTTP. And then, of course, in the end, we want to have the nice new model, which is much nicer than the model that we have currently in Play. We want to have that on the surface so that you can actually use all those types, right? As long as as Play has to keep the APIs stable, we can't surface this nice stuff. So what is happening if Play moves onto Akka HTTP just like that, then we'll have a nice parsing layer underneath, build a really shiny proper model, and then we'll call toString on all those types to funnel them through the Play APIs, which is kind of, it pains me to just think about that. But so we want to change that in the future, of course. So these are the resources. We have a few minutes left. Thank you. Questions? Yes?
Roadmap,
time frame? Well, I always dodge that question. I might as well just do it now. I can't really talk about it too much. It's always tough because initially we thought, this is not going to take a long time, right? Just streams are well understood, let's just go out, 3 months, we're done, right? Now it's a year after we've had that talk, and things creep up, especially in this new reactive streams world, because there is a lot of stuff that we haven't really understood yet. There's a lot of research really happening in a certain way. How do you properly plug together those streams that have a backpressure channel? And tomorrow we're going to see exactly where all the complication comes from. So I'm not going to give you any date. The goal is, of course, ASAP. Everyone wants it. Play wants it. Everyone wants HTTP out, and we're working on it as much as we can. The goal is to have 1.0 out, the Akka HTTP 1.0 thing, currently at the end of Q1 this year, so there's not a lot of time left, 2 months or something. So we're currently kind of digging through the tickets. What are we still doing? What can't we do? It's tough. Yeah.
So you listed the 2 companies working already.
Well, the good thing is on Akka.io, we completely own the stack all the way through. So if there are any issues, and you're right that Netty has certainly had much more time to mature over time and really address small tickets and bugs and here and there. If we are aware of any bugs on the I.O. layer, we'll try to address them as quickly as possible because it's the base layer of everything. Currently, I don't think we have any known issues there, but it doesn't mean that we don't have them. I'm sure that Netty has more kind of special casing of Windows on a certain version where you have a certain bug. There has been a few things. There have been a few things that have crept up over the last 2 years that we have Akka.io now. But of course, you're right. We're not as mature yet just because we didn't have that time. But the goal is not to leave you alone with that, but to give us the chance to react quickly to the bugs that you find, rather than trying to fix something in Netty and work with them. Even though the cooperation with the Netty folks has been very nice, but it's still one level away, of course, right? So that's the goal. Yeah. Where you need that?
Where you want that?
Well, for example, if you implement an HTTP proxy, that's basically what it is. You just fold it up, and then you have a client, you have a proxy, which is taking in the request and sends it across another connection, and does the same thing on the other side. And then you need to, if the server is slow, you need to slow down the client because you want to be a transparent proxy in the middle, right? So there needs to be a way to transport back pressure across your own stack all the way into another connection. And if you have several proxies, which might well be the case, then it needs to go across machines, right? And you can do it. If you just connect TCP and all the stacks are properly kind of closed within the streams world, then this will work. And we're going to see, there's a chart on that tomorrow in tomorrow's session that deals exactly with that because it's very cool. Yeah, one more question? Okay, maybe we're out of time. Maybe we can take it outside. Thank you.